Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. So you can recall that in the last lecture we had discussed about the concept of variability or efficiency of an estimator, and we have seen that this variance or MSE, they are going to help us in finding out an estimator whose variability is as small as possible. But my next question is, you are trying to search for an estimator which has got the lowest variability. But what is this lowest variability? If you have estimator 1, you get some variability, and now you get another estimator, say estimator 2, whose variability is smaller than the first estimator. Now somebody comes with the third estimator whose variability is smaller than the variability of the first two estimator. So how long you will continue? So don't you think that you must also know that what is the lower bound of this variance by which the variability can be reduced? The variability will always be there in the real data set, but if you know that lower bound, you know that the variability of an estimator cannot go beyond this value, right. So in very simple words, if you can have an estimator whose variability matches with the lower bound of the variance, then you should be happy that you have got the best estimator. So that is what we are trying to discuss in this lecture, and this lower bound can be obtained by the Kramer-Rao lower bound, right. The name of Rao is the name of Professor C.R. Rao, who just celebrated his 100th birthday in September 2020, and yeah, he is a living father of statistics. So this was given by him, and yeah, means Professor Kramer is also there. So both of them had given this result. So that is why this is called as Kramer-Rao inequality or Kramer-Rao lower bound for the variance. So let us try to understand it. That's a very small topic. Okay, so let us begin. So we know that the variance of an estimator theta hat of theta is defined as, say, expected value of theta hat minus expected value of theta hat whole square, that we know. Now I try to first state what is the Kramer-Rao lower bound and how it is related to efficiency and what is this result. So in order to use this Kramer-Rao lower bound, there are some conditions which have to be satisfied. So now we try to understand them one by one. So let x1, x2, xn be a random sample from a distribution with fx theta, some probability density function or probability mass function, whatever you want. Theta belongs to the parametric space capital theta, and g theta is the parameter that we want to estimate. So g theta can be theta, or that can be a function of the parameters involved in it. So the Kramer-Rao lower bound, which is briefly called as CRLB, provides a lower bound for the variance of any unbiased estimator of g theta. You had seen that in the earlier lectures we have considered 3 or 4 possible estimator of the parameter mu from a normal distribution, normal mu with sigma square equal to 1, and then we also had found their variances, right. So the simple question here is suppose delta x as an unbiased estimator of g theta. That means expected value of delta x is equal to g theta. Now my question is this: the variance of delta x will be greater than or equal to what? That I don't know, and that is the answer which is given by this Kramer-Rao lower bound, right. And so obviously that can be understood very easily, that if an unbiased estimator has got a variance which is equal to the Kramer-Rao lower bound, then it is the best estimator that can estimate the parameter g theta. So obviously now the simple rule is, closer the variance to CRLB, better is the estimator, and that is why this Kramer-Rao lower bound is very popular when you are trying to work in real data science. So there are a couple of assumptions which are needed for the validity and the mathematical derivation of this Kramer-Rao lower bound, although I am not going to do here the mathematical derivation, but surely when you want to use it, you have to first make sure that these assumptions are valid. Usually people are not bothered about it, and when they try to use, and if any of this assumption is not satisfied, surely that will give you a wrong result. Right. So, the first assumption is the range of the distribution of x does not depend on theta. That is very simple. Yeah, for example, if you try to see the range of the binomial distribution, binomial NP is x 0, 1, 2 up to n, which does not depend on p. Similarly, the range of Poisson distribution is like x goes from 0, 1, 2 up to dot dot dot, and this does not depend on the lambda. So, and similarly, if you try to see in the case of normal distribution, also you have two parameters mu and sigma square, but the range of x is between minus infinity and plus infinity. But this does not mean that all the estimators have got such a thing. An example is the uniform distribution, say 0 to theta. So, in this case x lies between 0 and theta, and the form of the PDF is 1 upon theta. So, you can see here in this case the range is going to depend upon the parameter theta. So, we are not going to consider this type of situation. Okay. So, the second assumption is that this g theta is differentiable, and third assumption is this f x given theta is differentiable, and fourth assumption is the derivation of left hand side of this quantity, that is the integral f x theta dx exists and can be obtained by differentiating under the integral sign. You know that you cannot take the integral, the differentiation sign inside the integral sign just as such. There are certain rules which are governing it. So, we are not going into that detail, but we are assuming that all these conditions are going to hold true, and believe me, with most of the this standard probability density function and mass function, these conditions are generally true. Right. So, now the Kramer-Rao lower bound is defined as follows. Then the variance of delta x, which is an unbiased estimator of g theta, is given by this quantity. This is g prime theta whole square divided by n times expected value of partial derivative of log of f x theta with respect to theta whole square. Right. So, this g prime theta is the first derivative with respect to theta, right, something like what you say d by d theta of g theta. Right. So, now you can compute these quantities, and this value on the right hand side, which is here, this is called as a Kramer-Rao lower bound, and this indicates the maximum achievable accuracy. Right. So, another form of this variance of delta x is given by this quantity, where this denominator is given by minus times n, expected value of second partial derivative of log of f x theta with respect to theta square and its square. Right. And in both the cases, we are assuming that the left hand side of this integral integral f x theta dx equal to 1 exists and can be differentiated 2 times under the integral sign. Otherwise, you will not get here the second partial derivative. Right. Now, in this form, you can see here this function, expected value of partial derivative of log function with respect to theta whole square. This is called as Fischer information, and it is usually indicated by the function I theta. And the other form is given by like this, which is the same thing that was coming in the alternative form of the Kramer-Rao lower bound here in this case. Right. So, now this is also called as Fischer information and indicated by I theta. So, this quantity is called as Fischer information in the sense because it is trying to give us the information that is contained about theta in x. So, obviously, if the information contained is high, then the achievable accuracy is also going to be higher, right. And mathematically, you can see here that expected value of the square of first partial derivative of log of f x theta is the same as the variance of first partial derivative of log of x theta with respect to theta, right. So, that you can see mathematically. And so, now you can define the Fischer information like this. So, now what you can do here, you already have got the definition of minimum variance and bias estimator, uniformly minimum variance and bias estimator. So, what will happen? That variance of uniformly minimum variance and bias estimator will be greater than or equal to CRLB, Kramer-Rao lower bound. And if this become exactly equal to Kramer-Rao lower bound, then you have the best estimator. So, in case if you want to compute the efficiency of an unbiased estimator delta x, then it can be obtained using the concept of Kramer-Rao lower bound as the ratio of Kramer-Rao lower bound divided by its variance. Right. So, let me try to take here an example to show you that how these things can be computed, so that you are confident that these are not very difficult thing, right. Suppose we have got a random sample x1, x2, xn from a Bernoulli distribution, say binomial 1p, and you can see here that if you want to find out the joint density function of x1, x2, xn, then because they are independent. So, you can write down f of x1, x2, xn as the product of this f of xi, right. I goes from 1 to n. From there I can write down here this joint function f x for a given value of p. And now, if you try to take its natural log, that is straightforward, you try to differentiate it partially, and you will obtain here this expression, and then you try to square it and then try to take its expectation. This is the same as variance of this quantity inside the parenthesis, and this is same as which you have obtained here, variance of this quantity x upon p minus n minus x upon 1 minus p. And if you try to compute this variance, that can be obtained very easily. This will turn out to be 1 upon p into 1 minus p, and this is the information about the parameter p, right. So, now you, in case if you try to find out the Kramer-Rao lower bound, this can be obtained just by substituting all this expression, and it will turn out to be p into 1 minus p upon n. And you can see here this the first derivative of gp with respect to p is here 1. And now, in case if you try to see here, this is the Kramer-Rao lower bound for this estimator. And now, in case if you try to recall that we had obtained that small p can be estimated by the sample mean of x1, x2, xp in the case of binomial distribution, and in that case if you try to find out the variance of x bar, this will come out to be 1 upon n square variance or summation of xi, and this can be obtained here as a p into 1 minus p upon n. And you can see here both the variances are the same. That means, the Kramer-Rao lower bound and the variance of x bar, they are the same. So, now you can be confident that you can estimate the population proportion of a binomial distribution by this sample mean without any problem, and that is going to give you a good value. And similarly, if you try to take one more example from the continuous random variable. So, let x1, x2, xn be a random sample from normal distribution with the mean mu and variance sigma square, whose PDF is given by like this, that you know. So, now we have here two parameters mu and sigma square. So, we need to find out the Kramer-Rao lower bound for mu and sigma square both. So, we need to do the same thing. So, if you try to find out their joint density function, and then you try to take its log, and then you try to differentiate it first with respect to mu, and then with respect to mu square, you will get here these quantities. Well, I am not solving it here because they are pretty straightforward thing. And then if you try to find out the value of information based on this mu, this will be simply the minus of expectation of this quantity. This comes out to be here 1 upon sigma square. So, the Kramer-Rao lower bound for any unbiased estimator of mu is coming out to be 1 upon n times information, which is sigma square upon n. And now, if you try to recall, earlier you had estimated the value of mu by x bar, and whose variance was coming out to be sigma square upon n. That means the variance of x bar and Kramer-Rao lower bound, they are matching. So, that means if you want to estimate the parameter mu of the normal population, then x bar is the uniformly minimum variance unbiased estimator of mu. And similarly, if you try to do the same exercise for the sigma square, you try to write down the log of this fx mu sigma square, then you try to differentiate it with respect to sigma square, then you try to take the second partial derivative, you will get here these expressions, and based on that, if you try to substitute these expressions in the value of I sigma square, you will get here the value here 1 upon 2 sigma raised to the power of here 4. So, the Kramer-Rao lower bound of any unbiased estimator of sigma square will come out to be twice of sigma raised to the power of 4 upon here n, right. And now, I come to an end to this lecture, and you can see here this was a very short lecture, but very informative. Now, you have got the idea that okay, somebody can propose any estimator for estimating the any parameter, and suppose this is an unbiased estimator, then in that case you can compute the Kramer-Rao lower bound and can judge whether the values which you are trying to obtain for an unknown parameter are good or bad. So, I will request you try to take some more examples from the book, try to solve them mathematically. These are very simple exercises, and I will see you in the next lecture with next topic. Till then, goodbye.